So chapter 8, we're going to talk about energy, and this is different kinds of energy that you learned. And this energy is called the potential energy. Okay, so last time in previous chapter we talked about kinetic energy, and kinetic energy basically is associated with when you have an object that's moving. When the object is moving with a velocity, then it contains energy, and that energy we call that kinetic energy, and we use this symbol K to indicate that's kinetic energy. So what is the expression for kinetic energy? That's 1/2 mv squared. So we can see that this expression of kinetic energy basically depends on the mass of the object and also the velocity, how fast the object is moving, v squared. So this is always a positive quantity, right? Now, what you're going to learn in chapter 8 is that potential energy basically does not depend on velocity. However, it depends on the arrangement within that system, and also depends on the separation of the particle within that system. So it is about separation. It's about the arrangement within the system. Okay. So what is the expression for potential energy, and what is the symbol that we use for that? So for potential energy, we use this capital U to indicate that that's a potential energy, and it depends on what kind of force involved. Then you will have a different expression for potential energy. For example, whenever you have a force, that force is going to associate with the energy, with the potential energy. So it really depends on the kind of force that you involve. It will not always be this simple as 1/2 mv squared. So in other words, you can see that your kinetic energy only depends on velocity, but for potential energy, it depends on what kind of force that is at work. Okay. Now, what kind of forces we have learned so far? We have learned gravitational force, and also normal force, frictional force, elastic or spring force, right? Okay, or drag force. So all these kind of forces, they will produce they will have a different expression for potential energy. Okay, and so let me just rephrase it again. That potential energy is the energy that can be associated with the configuration of a system of objects that exert forces on one another. So whenever you have forces, there's potential energy involved. Okay, so and we mentioned that there's a gravitational force, so that the gravitational potential energy, we use UG to indicate that's gravitational potential energy. We also mentioned, in previous chapter, we mentioned about spring force. So there's potential energy that is associated with the elasticity of the spring, which is called that spring potential energy. So you can see that you have gravitational potential energy, you have spring potential energy, and those are due to the kind of force that is, that exert forces on one another, the gravitational force and the spring force. Okay. And last chapter, we mentioned that there is a work kinetic energy theorem, and that is, what is the work and kinetic energy theorem? How does the kinetic energy change within a system? How do we accomplish that? If we want to change the kinetic energy of the system, how do we do that? You have to apply the force, right? And the force that's going to do work. So you have to apply force that does work in order to change the kinetic energy. And that is based on the work kinetic energy theorem. So that is delta K is equal to work, right? So that's equal to net work. So in other words, whenever there's a net force when there's a net force that does net work and that's non-zero, is going to be used to change the kinetic energy of the system. Now, likewise, when you want to change potential energy, okay, regardless whether it's gravitational potential energy or spring potential energy, work has to be done. And how do we do work? You have to apply a force. So the force is applied to do work to change the potential energy. And what we found is that the change in potential energy is equal to negative work that's done by the force. So you can see that This delta K is equal to the is equal to net work done by the force, and this net work can be positive or negative depending on whether the energy is added to the system or remove energy from the system. And likewise, if you want to change potential energy, then either by changing its configuration within the system or change the separation of the object, then work has to be done. And how do we do work? You have to apply a force, and that applied force is going to do work, and that net work is actually have a negative sign in front of it. So the change of potential energy is equal to negative work done by the force. Okay, and we mentioned that there are two different kinds of forces that we learned so far, which is one is gravitational force and one is spring force. Now both forces, they share a common feature. They are what we call the conservative force. And I'll explain what I mean when I say they are conservative forces. When you have a force that is conservative, it means that energy is conserved. Okay, and also the implications of that, or the consequence of that, is that when you have a force, when the work done by a conservative force is path independent. And I'll show you an example. What do I mean? Path independent. Now, you will introduce some other forces that are non-conservative, and when it is non-conservative, which means that it is path dependent. For example, drag force, spring, the friction force. All these forces are considered as they are non-conservative. Why do we say that they are non-conservative? Just by the word we use, non-conservative, which means that energy is not conserved. It takes away energy. Whenever you have the friction force, that friction force takes away energy, so that it lowers the energy of the system. So this kind of forces are considered as non-conservative. And when you have a non-conservative force at work, which means that the work done by these non-conservative forces are path dependent. Okay? Okay, so what do I mean when they are path dependent or path independent? So let's say you have an object. Now let's say it experiences gravitational force. So we already mentioned that gravitational force is a conservative force. When you have conservative force, it does work that is conserved. Okay, and let's say you have an object and you let it drop. Okay, so the displacement from this point, let's say this is initial height, let's say is h, and then goes to the ground. That's the final height. Let's say is 0. So during this move, when you let the object drop, during this move, it goes from height h and then go to the ground. So the direction of gravitational force is downward, and the direction of displacement is also downward. So in that case, what is the work done by this force? What is the work done by gravitational force? From chapter 7, work done by gravitational force, that will be F dot D, right? Exactly, F dot D. So you have F, that's mg, and then dot D. So your D, so you have your mgd. And then because they are in the same direction, so the sign of the sign between them, the angle between them is 0. So you have mgd cosine of 0. So that just gives you mgd, right? So this is the work done by gravitational force. So let's say you have this elastic object, and then we let it drop, and then it drops to the floor, and then it's going to come back up because it's elastic. So when it touches the ground and then goes up go to the same height, what will be the work done by this force? So in other words, excuse me. In other words, you drop the ball and that's elastic, so you can actually jump off the ground. So we let it drop, so it go down during this segment. The work done by gravitational force is mgd, that we know. And then it's going to, because it's elastic, so it's going to come back up. And then when it reaches the same height, then what is the work? So let's say this is WG, segment 1. This is WG, segment 2. What is segment 2? What is the work done by gravitational force during this move? That will be negative Fg, gravitational force, and then times d, right? Okay? So what is the net work when you go from this point and then back to this original starting point? That will be 0, right? Because when you add those two together, one is positive and one is negative. When you add them together, the net work is Wg1 plus Wg2, and that will just give you 0. Okay? What does that mean? It means that if this is your starting point, and then when it reach up, regardless how they go from this point to, so you take that as your initial point, and then you take this as your final point. You can see that your initial point and the final point, they are at the same height. What does that mean? It means that there's no change in potential energy. Okay? Because the net work done by this gravitational force is 0. And then based on this equation, we know that when the net work done is 0, there's no change in gravitational potential energy. So the gravitational potential energy at this point, as opposed to the gravitational potential energy at that point, that has to be the same. Any questions so far? What does that mean? Okay? So it means that, so what does this example tell you? This example tells you that as long as you have the initial point and the final point, they are at the same location or at the same height, there's no change in potential energy because the net work done by that force, by that conservative force, is 0. Okay, so this is, we take that example, use the gravitational force as example. You can also use the spring force as example as well, because spring force you can bring it, extend it, or you can compress it. It will be the same as long as the initial point and the final point, they are at the same position. Then there's no change in potential energy. And later we're going to describe, what is expression? We're going to derive the expression for the gravitational potential energy and also the spring potential energy. Okay, so this example illustrates that the work done by conservative force is path independent. It is path independent because you can go from this point and then come back up. And likewise, you can actually drop this ball like this and it comes back up. So you have another track that go from this point and go up there. As long as you reach the same height, the final position and the initial position are at the same height, there's no work done by the gravitational force or by the conservative force. Okay? Or you can have something like just like this. Okay, so you can see that this one has a different tracks, right? And the features that you want to look for is that let's say this is your initial height, okay? And this is your final height. You can see that. How many different tracks are there? 1, 2, 3, 4, right? So 4 different tracks, and you can see that they have a different distance from this point to that point. But vertically, what is the distance? What is the separation from this point to that point? That would be just this, right? Although the rim, they have a different length on this 4 different lengths, but vertically, the vertical separation between this point and the ground, they are the same. What does that mean? It means that when you have an object sliding down from different tracks, although the horizontal distance might be longer, let's say this one is longer than the other one, but then vertical separation stays the same. As long as the vertical separation stays the same, then what will be the work done by gravitational force? So, in other words, you have a situation like this. So this is the starting point, and this is the final point. And from this starting point to the final point, this is, let's say, vertical separation, let's say, is h. And then you can go from this point, you can have this track, you can have this track, or you can have, I don't know, like this track and that track. So you can see that, let's say, take for example, this is 3 different tracks. The features that we have here is that horizontally, this one, the distance, or not the horizontally, but distance-wise, this distance is definitely much longer than this distance. It's also longer than that distance, right? So the distance that the object travel are different, but vertical separation, they are the same. So what will be the work done by gravitational force in this case? So let's say you have an object that has a mass m. What is the work done by gravitational force? If we assume that these tracks are frictionless, so what will be the work done by gravitational force in this case? The expression for gravitational force? Yes? mg, right? So that's a gravitational force. What about work done by gravitational force? That will be just mg. So let's say you have your Fg. So by definition, the work done by gravitational force will be equal to gravitational force, the scalar product of gravitational force and the displacement. In this case, your gravitational force of this object, it is downward. So this is your mg. What will be the displacement that actually contribute to work? The displacement from here to here, or what is the displacement? It will be just from this point to that point, right? Remember, because we do a scalar product, so the force and the displacement have to be in the same direction to contribute to work. This displacement is horizontally, has nothing to do with vertical displacement. So this segment does not do any work. Now, when it comes to this region, we know that you have this, you can find a projection to see what is the vertical, the vertical displacement of the object that goes through. So it consists of this part. So this object consists of two parts. One is a horizontal displacement, and one is a vertical displacement. Because gravitational force is in the vertical direction, so horizontal displacement does not contribute to work. Only the vertical displacement contributes to work. So just based on this diagram, you can just directly take the initial point and the final point. That h would just be the amount, the displacement that will go into calculating the work. So that will be your mg and then times your h. And it's a positive quantity because gravitational force is downward and this vertical displacement is also downward because it goes from a certain height to a lower height. Okay? So you can see that this particle, when it go from this, this first track, or go to the second track, or go through the third track, they will all have the same gravitation. They will all have the same work done by gravitational force because gravity does not change. Your mg, the mass of the object does not change. You still have your mg. Vertical displacement, it is the same for these three tracks. So that's why the amount of work done by gravitational force stays the same for these three different tracks. Okay? This is when you are not dealing with a frictional force. What about if there's a frictional force involved? Let's say these tracks are not frictionless. It actually not comes with the friction. So in that case, the distance that the object travels does make an impact, depends on how much work is done by gravitational force because energy will be taken away by the non-conservative force. So that's why we say that drag force and also the friction force, they are non-conservative force because they take away energy. And the amount of work done by them is actually path dependent. So in other words, when you have an object, let's say you have an object that's sliding across the floor, and then the floor is frictionless. There's a friction between the block and the floor. So when the object is moving, you can see that it does not. So the velocity, is going to decrease. Why is the velocity decreases? And that's because when it goes from this distance, there's energy that being dissipated or being taken away by the frictional force. So that's why this object actually gets slowed down, right? Okay, and that's why the non-conservative force, the amount of work is done by non-conservative force is path dependent. The longer that it travels, the more energy that's being taken away from the system, and that makes sense, right? Okay, so the important concept about the work done by a conservative force and the work done by non-conservative force is that one is conserved and the other one is none. So once energy is taken away, that's just being dissipated. You can't you can't get it back. But then for gravitational force, we know that when you go from here and then comes back up, the energy is conserved. It it doesn't change whatsoever. Okay. So that's that. Now, we mentioned the two forces. One is the gravitational force, and one is spring force. So what is the expression for the potential energy that's involved when you have these two different forces? So let's look at the expression. So the gravity, we know that it's just mg. And the amount of work done by gravity, we mentioned that it is mg times d. But then we also, let's say, by definition, this is what you learned from chapter 7. F is equal to F dot d. This is when you have an object. When you have an object and then a force is exerting on the object with a constant force, then the work done by the force is just F dot d. You can just use that because the force is a constant and the separation is known. You can use F dot d. Okay, so what about when you have an object? Now, if we bring this object and it experiences gravity, so you have downward gravity, and we're going to bring this object from this initial point, go to, let's say, the final position. So let's say going from this point, we move this object to this point. So you can see that the distance now is not a constant. So we're going to actually move this, we're going to move this object, and then bring it from this point all the way to the final destination. So the displacement now actually changes. So you cannot just use F dot d unless you know the separation between these 2 points. That's it. We don't know the separation of these 2 points. So these two, the initial position and the final position, they are just dummy variables. So how do we find the amount of work involved that is done by gravitational force? So you have your WG. We want to find what is the work done by gravitational force. So that's just go by definition. This is the definition. So what is definitional work? The work is equal to F dot d, if you remember. So let's say this is the equation. The amount of work that's done when you have a force that's a variable force, then you have to use F as a function position, and then integrate along the displacement, and then starting from initial position to final position. So this is the work done by the force. So we can use this definition to find out what is the work done by gravitational force when you have position, vertical displacement is changing. So now what we have here is that you have your Fg, okay, and then you have your dy. Instead of using dx, we use dy because we're going to move in this direction, okay? And then your position is from initial position to your final position. So in that case, let's look at this equation, okay? So what we have here is that this is the work done by gravitational force. And we're going to utilize, because we want to find the expression for gravitational potential energy. So let's say the change in gravitational potential energy and the work done by gravitational force, they differ by what? So delta U and WG, they differ by, this is a change in gravitational potential energy. This is the work done by gravitational force, huh? By a sign, right? So that's a negative, right? So in other words, the change in gravitational potential energy is equal to negative work done by gravitational force. So what we have here is that we know that this is the expression for the work done by gravitational force. So we're going to say that replace Wg with this expression. So your delta U, the change in gravitational potential energy, is equal to negative, and then you have your gravitational force and then displacement. And your displacement starting from initial point to your final point. So that's the integration. And this, if you're not familiar with integration, this is just for your information. So you can see that your mg, your gravitational force is just mg, which is a constant. Okay, so if that's a constant, you can just bring outside the integral sign. So you have negative, copy that down, negative, and then you have your mg, and then you have your dy, and you're starting from initial point to the final point. So what we have here is that you have your mg, and then what? For those of you who know how to do this. So we integrate dy. So the integral and the d, they just get canceled, right? So what do we have here? that will be just y. So you have your negative mgy, and then you have the lower boundary, the upper boundary. So what we have here is that you have negative mg, the final position, and then minus, and then because you have the negative side, so negative negative becomes positive, plus your mg, and then yi. Okay? All right, so what we have here is that you have the change in gravitational potential energy. Now we know the expression. What is the expression? It's just like the difference between the mg, the mgy and the mgyf. So what we can do is that if we write it out, the delta will be the final gravitational potential energy minus initial gravitational potential energy. Then your delta U can be expressed as your UG, the final minus UG, and then initial, and that's equal to negative mgyf, and then plus your mgyi. Now a lot of time we define the potential. We define one of the potential to be 0, and the other potential can be found just by using this, because potential itself is not very meaningful. It is a potential difference. The potential difference that has a meaning, okay? So in order to find the potential difference, you have to actually define your reference point. So in this case, by convention, we usually define the initial point to be 0. Let's say on the ground, we define it to be 0. And then at the same time, we define the initial gravitational potential energy at that point to be 0 as well. And you'll find that it actually doesn't really matter how you define this. You can define it to be 5 joules. You can define it to be negative 5 joules, and the value at that point will just be readjusted according to your reference, your reference point. So you can see that the potential energy only depends on the difference. The absolute value, the absolute value of the quantity is not really doesn't really give you anything. Okay, so in this case, what we're going to do is that we're going to plug in to whatever information we have. If we define at this point to be, let's say, the starting point to be 0 location, 0 altitude, and then the gravitational potential energy at that point is also 0. What we have here is that you have this one goes away, right? So your gravitational potential energy, and we're going to drop the, we're going to drop the F here, and just have the UG. So the expression for gravitational potential energy is equal to, and what you have here is that, and I think I'm missing a sign. Why am I missing a sign? Let me see. Yeah, we have this. Oh, okay. Do you know why I'm missing a sign? Because, can I go back here? Sorry. So this is definition. So your delta UG is negative, and then FG dy. So, and your FG is let's say negative mg, because it's going downward. So this is your mg that's negative, and your dy is actually in that direction. So they differ. So they differ by a negative sign. So what we have here is a negative. So let's just do it this way. Right? Did you get that? Yeah, I forgot to, this one is going down. The integration is going up, so they differ by a negative sign. So when you do this f dy, then there should be a negative f dy. So negative negative, then this becomes positive, and then you have this. So again, sorry about this. So that you have this, and then this. Okay? This is just, because they differ by 180 degrees. So when you do FG dy, then the FG dy cosine 180. So that just gives negative. So that's where the negative comes from. So once you have here, so again, so you have, so this is positive and this is negative. All right, so on the right-hand side, you have the mgyf minus mgyi. On the left-hand side, you have the final gravitational potential energy minus the initial gravitational potential energy. And we define the initial gravitational potential energy to be 0. At the same time, we define this ground position to be 0. So what we have here is that this is the gravitational potential energy at height, at this final height, and that's equal to, because you define this to be 0, so that just become mg, and then instead of yf, we drop the f, that's the final, so it's just mgy. So this is expression for gravitational potential energy. Okay, so that's just mgy, and you can see that it really depends on your y value in this particular instance, because your y here is above the reference point. So the energy, the gravitational potential energy, is positive because it's above the reference line. If you have, however, if the object now is going down, in that case, and if you define this still to be your 0 reference point, anything below has to be negative. So in that case, your y here will be a negative value. So you have a negative gravitational potential energy. What does that mean? It means that potential energy really can be positive or negative. As opposed to when you have a kinetic energy, it's always positive because kinetic energy is 1/2 mv squared. But then when you have gravitational potential energy, it really depends on your reference point. Anything above the reference point is positive. Anything below the reference point is negative. Okay? So you have a gravitational energy that's mgy. So in that case, we also know that your W, your delta U is equal to negative W. So you can see that the work done by gravitational force is negative mgy because they differ by a negative sign. And that's where we started with. Okay? Any questions so far regarding this? So sorry about that. I forgot to, because we're integrating along a different, along this, but one is upward. So you have to take that into account. Okay. All right. So this is the expression for gravitational potential energy. What about the spring potential energy? When you have a spring, there's a spring force at work. That force is going to produce a potential energy, and that potential energy we call that spring potential energy. And spring is, is also spring force is a conservative force. So we know that it also follows the rules that it is path independent. Okay. So how do we find the work done or the gravitational potential energy that's done by the spring force? So we're going to again utilize this expression. This is for a generic case that you have a force and there's a displacement. This is the amount of work done by that force. So now what we're going to do is that we're going to find the spring force, that the gravitational potential energy that is done by the spring force. So this is what we call the spring potential energy. So this is equal to, and that's equal to negative W. Okay? Because that's by the similar to the work kinetic energy theory. So when you have the work done by spring force, it is negative to the gravitational potential energy done by the spring force. So then we have negative here, and then you have the force that will be the spring force, which is actually now a position of is a function position, and then dx, and your x is initial position to the final position. Okay. So what we have here is that what is the expression for the spring force? The expression for the spring force? Negative kx, right? Now the variable here is the x, so we're going to use the x. So it's negative kx. So in that case, so we still have that negative here that comes from this, and then your f here is negative kx, and then you're going to dx. Okay, and the range is from xi to xf, the final position to initial position. Okay, and now what we have here is that your delta U S is equal to, you can see that negative, they cancel each other. So now what we have here is that you have the spring constant, which is a constant. I'm going to bring it outside the integral. So you have your k, and then you have your x dx. From xi to xf. What is x dx? is 1/2 x squared, right? So you have 1/2, and then you have your k, and then x squared. And then you have the range, that's xi to xf. So we're going to plug in the boundary. So what we have here on the right-hand side, you have 1/2 spring constant, and then the final position of the spring minus 1/2 k initial position of the spring. And then your delta U, again, is the final spring potential energy minus initial potential energy. So I have US, and I'm going to use the F to indicate that's a final, and then minus US, and then initial. Okay? So, and again, by convention, we usually define this initial point to be 0, and the energy associated with at that point is also 0 as well. Okay? So in that case, you will have your xi is 0, and then usi is also 0. Okay? This is the spring potential energy at this point. When this point, we define it to be 0, then we also let this to be 0. So what I want to emphasize is that potential energy only depends on the difference. It doesn't really matter whether we choose this to be 0. You can choose it as phi. You can choose it negative phi. It doesn't really matter. It's just that the final potential energy will be readjusted according to your initial value. And in this case, for simplicity, we just define it to be 0. Okay? So in that case, this is 0. This is 0. So what we have is that the spring potential energy, okay, any displacement in relation to the initial point would just be 1/2 k x squared. And you can see I dropped the F because that's the final position. So this is the expression for the spring potential energy. And if you recall from last chapter, we find work done by spring force, and the work done by spring force is actually equal to negative 1/2 kx squared, which is consistent with what we have here because your US and the work done differ by a negative sign. So what is negative 1/2 kx squared? Then the spring potential energy is positive 1/2 kx squared. Okay, and potential energy is energy, so it should have a unit of joules. All right, so let me just write it down. So UGY. So you have this expression for gravitational potential energy, and you have that expression for the spring potential energy. Yes, yeah, because they are in units of energy, which is joules. Okay?